So the next thing is how you explain. So once you have an operator, we if we have a basis that we can use to explain all your vector in that vector space, then obviously you want the operator to also uh, expand in the same basis. And the idea is that that expansion will not result in the vector like the expansion of a function, but instead will be a matrix. Right? It depends on the number of bases. N as finite number n by n, you have an n by n matrix. If infinite, you have a square matrix with infinite dimensions. Okay, so that so basically you want to uh, the operator on a basis first. Phi using following your textbook notation phi, so the index mu, right? And generally, this will give you another vector, whatever that vector is. You want to, but then you want to expand that into um, all the same set of bases. And we already seen how you do that, right? So, let's just write what we did before for a uh, vector or function expansion in a set of bases. It's just simply sum over. Let's just follow the same notation instead of using I and j as we did before, using this grid letter like mu and then in basis of mu. So you want to expand that in phi nu, and the idea is just do the projection of f on mu. So nu. That will give you the scalar part will give you the projection of all the components of F along the phi nu along the phi nu basis. Okay, so that's the expansion that we did before, right, last time. And the same thing, so this will be a vector just like F, where A, the operator operates on phi will give you a vector. This vector is generally not uh, a particular basis is has to be expanded in this set of matrix itself. Okay, so what we do is following the same way. So come over the set of all the bases and then the projection of phi u, right? And then F is this one. This is the vector that we try to expand, right? So we should A phi u and then phi u. Right? So that's straightforward coming from what we did last time. We just say that we expand this vector, which is A operate on the basis. So that will give you this one, right? So this is, we can give you a name. So this is just a number. Basically, you can say that this is, we'll give you a name, A mu. Okay, so this number has two indices, as nu and mu. So it's representing a scalar product of phi nu and A operator on phi mu. Okay, so, and so right, so that's one way to look at that. So this is the operator on one basis. Now you can consider the operator A operator on an arbitrary function psi, right? This in this case, psi is given by the textbook topic is C mu, the coefficient C mu by mu, and you know how the coefficient is just like following the same rules. So this is just m over nu and by nu and sine. Right, so C nu is this. C sub nu is this. C sub this is mu. C sub mu is this. The scalar part. Okay, and now we want to A operate on that one. So basically, um, this substitute this into here with this sum over mu, C sub mu, A operated by mu, side phi mu, right? And now we already have this one, so we can substitute this in, or this into this, or this into this. We actually probably will do it both. Sum over mu, and this involving another sum over mu, C sub mu, and A mu, mu, and phi mu. Right. And if we uh, give a name of this one, and I think your text will call it time. Define this is just another function or another vector, right? And that is we call this is some of the mu, b mu. So basically, whatever the coefficient in front of the phi nu, we call it b nu, b sub nu. So obviously, by comparison, the b sub nu will be equals to phi sub mu and a mu, right? You can see that, right? So you just rearrange that order of this summation and put C over on the right. To do that, it's just make it in the form of a matrix multiplication. If you represent C mu as a column vector, B mu as a column vector, then this becomes a square matrix. A square matrix multiplied by a column vector give you another column vector, right? So this basically just like a matrix multiplication, and so this a mu nu will be a, so you can say that a mu nu is the matrix elements of the original vector, original operator A, right? So and just like what we did before, it's just this is defined as phi mu mu, right? Basically, you can say it's the operator, the nu and mu component of this operator. Right? This is operator, but after you do the basis expansion, and then you get the nu and mu component, the nu and mu element will be this number A, right? Then the definition is this scalar product. And now once you have this matrix, then the the operation A on the vector side is just basically use the matrix representation of psi, which is just a column matrix, a column vector of C, and then the matrix basis representation of X, which is a matrix A, and then do a matrix multiplication, you get B, which is the column vector that, and the basis expansion of this vector, which is A operated on psi, would be a chi, right? So basically transform this operation A operator on a vector, which may or may not be complicated, but once you do all the expansion, all the vector and operator like then all this operation is just like matrix multiplication to make it straightforward. Is that okay? So that's the way to do it, right? And another way to look at that is now you have A5. Uh, C sub mu is this one, right? Um, and the A sub mu is this one. So you can actually uh, like substitute all these into here. So chi is equals to A sine, right? Um, equals to now we substitute everything here. So sum over mu. C sub mu is this one. Mu sine by mu. That's wait, no, this we wanted this one. So this is this one. A and A new mu is this one. By mu. Okay. And then by mu. But that's this one in the final. But you can write it this way, so without all these coefficients, without defining all these coefficients, just substitute all the explicit scalar product uh, in here. Actually, by writing this, I'm actually starting to use the Dirac notation. And the way to do it is when you use the Dirac notation, you basically like changing all the functions as vector, as cat vector, right? Basically, as cat vector. And the the trick now is to rearrange them in a way that we have seen that before. So you like yeah, find new. So this is just a number, right? You can put it on the other side, right? So you find psi new, like find new, and then this object find new, and find new, right? Let's just put this number on the other side. That's fine. And then this is also a number. You can put it on the other side. Find new. So, and there is sum over mu. It's say it's sum over mu, and sum over mu, right? And now the trick is that in Dirac notation, this is like you have A and psi. Now what you do is it's like one out of space. So you start with A and psi. You say that let's see, it's A and psi, right? You want to do basis expansion of this operation. A operates on the vector psi. So in Dirac notation, this becomes a cat vector. Um, so all you need to do is insert this identity, which you can say insert one in front of A, so sum over mu by mu by mu. That that's that's one, right, in the Dirac notation. And then you have A in here, but A sub is basically insert another identity. So summation mu, right, over mu, and yeah, yeah, that's right. Somewhere for new, yeah, new, new, and then the in front of this cat vector sign, right? And then you see that this one is just basically this one after you take the summation out, which is fine. So you take whatever the order summation that doesn't change. And then there is doing some kind of notation abuse abuse of notation. So you consider this as a scalar product, right? This is scalar product like this one. Okay. This now this becomes a number. This becomes another number, right? And then you get the expansion right away. So the Dirac notation has this trick, which works, and then it gives you the correct result. But you see, to see the correct result, we actually went through all this expansion, which is not difficult at all. We went through this definition of expansion and the basis uh, with function that defined by the scalar product. You can went through and then get this expression this way. But then using Dirac notation is just all you need to do is just insert uh, appropriate identity in, in between operator and the vector. And okay, so that's one way to look at that. I mean, it's not like this is not rigorous. I can like let me see that. This is not rigorous. The rigorous way is this way, but this has the. I mean, this can be used as memory. So if you don't want to, you forget about how to do that. All these coefficient, how you get the coefficient, and you don't want to rederive everything from the beginning, start from the beginning, which takes slightly longer. And you can do this trick by just inserting this identity, and then now figure out what the coefficients are. So this is like this coefficient, uh, which is the matrix elements of A, is sandwiching between phi mu and phi nu this way. And this is coefficient of the expansion of this psi function, right? And now you figure out all the coefficients this way. So it's slightly faster. Right? You like to do that. Right, okay. So that's Dirac notation. All right. Um, uh, the one more thing is, I mean, it's also like Dirac notation. It's going back to going back to here, going back to here. Yeah, right. This is how after we get the expansion. This is if you look at this the original way. This is just a scalar product. This is just a number. But if you use the Dirac notation, then you add a strict line between the operator and the basis function, and then you can uh, reverse the order, like like putting this. Uh, like, I mean, this. Well, let's look at which. Let's see which equation we can look at because we wanted to get another representation. Actually this might be right to do it. Right. So, because we want to add this is operate on this one. So uh, well, actually this is already in this form because this is what we call the coefficient like a mu a du. This is a mu mu. The matrix element of A. Right. And you just uh, treat everything like that as something that operates on A. So the A operator is like operate on this cat vector. It's just this square object operate on uh, this vector. So you can say in that sense, you can see that A can be represented by sum over mu, sum over mu, and then by mu, this element A, mu mu, um, find mu. This is this object, right? A operate on that is this one, which is this one, operate on that one, right? And so this is in this writing in this way. This is just the matrix element, which is a number, and then these two, this is cat vector, this is a Bragg vector, but you multiply it in the other order. If it is this is on the level of operate on that, that becomes a scalar product as a number. If you reverse the order, this is like a column vector. This is like a row vector. If you have a column vector multiplied by a row vector, you get a matrix, right? And so this is like explicitly expressing A as a matrix, but the matrix now is expanding using all the spaces, the phi, the cat vector, the column vector multiplied by row vector. But you need the sum of all the mu and nu, all the bases, right? And the element of this one is just given by the original, what we call the matrix element of the operator, right? And which make it explicit, right? So when there's one way to look at that, which is may or may not be useful in calculation. That's another expression of this matrix of representation of A. Okay. Okay. Yeah. Yeah. Say it again. The last sentence. What's the second? I mean, the nuance index. You can call that whatever you want, right? Right. No, it doesn't matter what these are just dummy index. Right? It's just defined that way, right? So the new, find new, a new. I mean, uh, if I want to write it more explicitly, so if this is not even not key enough, there's some of a mu and mu, right? Then this is a column vector, like I said. So this is you have a you have all actually all this. If this represent in this the basis, the same basis that becomes zero, and only one is zero, or other zero. This is the mu, the new position. You get one, and again you get a mu, that number. And this is a row vector with a lot of zero, and then one at the mu position, and then all the zero versus zero, right? So this is a number, and this times that. This time that will be a matrix that is all zero except all zero except the position, which is one at the mu, a new position will be one. The rest are all zero, right? This multiplied by that, you give you this one. But it's not zero, but you just multiply A. And this, so this becomes A, mu. But you sum over all of them. You sum over all mu and mu. So basically, there are a bunch of these matrices that only have one element, and then you sum over all of them. So basically, you fill out the whole matrix with this as your matrix element. It's just another way to look at the same thing. All right. I guess the example is for Hermitian. I mean the Hermit polynomial. Okay. I think you can read that yourself. It's not difficult. Just calculating the matrix element by definition of scalar product. You just multiply, just do integration, and then use the whatever the basis functions are. Okay, so that shouldn't be difficult.